So as you can tell by the title, which always makes my job easier, we have Jessica and Mark here to talk to you about the evolution of what was sort of a novel and interesting new thing at Microsoft. Some number of years ago, those of you that are familiar with what EMET is, it became sort of an interesting but bolt-on solution to Windows to try to answer the question of what if we already kind of knew what to expect in attack space and extrapolated a bit from that to try to keep the bad things from having to get caught by the OS at all. So EMET became sort of a more offensively oriented defensive technique that had a fair amount of lifting to do to get it configured correctly and workable in an environment, but it had some remarkable capabilities. And then it sort of disappeared but didn't. Because in the world of Microsoft, one of the things we were looking at were ways to take EMET from the sort of flat pack IKEA model of security where you have to bring it all home, swear a lot, risk whatever relationship you're in, and then bolt this thing together into something that was actually accessible to everybody while providing even more security with lower latency and overhead. That's what Defender Exploit Guard is. So this is going to be your guided tour of how we got from something that was a great idea and maybe a little rough around the edges to something that actually made it into the integral core feature set of the latest version of Windows. It's also a great plug as to why you might want to update.
Thanks so much. This seems to be on. So thanks a lot for that awesome introduction. It kind of saves me a bit of my preamble about EMET. Mark and I are here to talk to you folks a bit about how we on Windows Security were able to learn from, finally embrace, and then modernize EMET for Windows 10. So just a quick show of hands, how many folks in the room are familiar with, have contributed to, love, have heard of EMET in general? I see a ton of hands, thanks. Some of them are plants, but a lot of them are legit. So for the few folks that maybe are less familiar with EMET, I pulled a couple of snippets out of EMET's Wikipedia page, which it does have. It was not created by me, I promise. That's just how much of a fan following EMET has. So EMET is a freeware security toolkit. As we mentioned earlier, it was built by Microsoft for Windows. EMET helps to provide a unified interface for you to be able to turn on, turn off, fine-tune a lot of Windows security features, exploit mitigations in particular. I want to talk a little bit about its initial release, its initial sort of conception. So EMET was released in 2009. If you think back to what was going on then, Windows was still on a pretty slow release cadence. I believe it was once every 3 years-ish around this time frame. But the overall point that we're trying to make here is that Windows release cadence wasn't fast enough for us over on Windows to be able to keep track with evolving attacker trends. This is kind of where EMET came into play because EMET was a toolkit on top of Windows. We were able to update it a lot more frequently. And the great news for Windows is that we were able to test out a lot of security features via EMET. A lot of those sort of tactical stopgap exploit mitigations that allowed us to react in real time to evolving attacker techniques in a way that we were not able to do using Windows at the time. And I think we noticed from the show of hands in the beginning, EMET is a super, super loved tool. Our customers loved it, sysadmins love it, security influencers, and enthusiasts alike. Huge fans of EMET. These are just some snippets that I was able to find, quick Google search. I want to draw your attention to a couple of the things on this slide. One, I think, which is really cool, is that EMET was actually part of the STIG requirements. And for those who aren't familiar with these, they're kind of a security baseline that's created that is actually followed by a lot of our really big customers, especially our big government customers. They sort of follow the STIGs as somewhat of a security baseline in terms of best recommendations, best practices from a security posture standpoint. And EMET was actually recommended as part of the STIG. Another quick shout out to Furman over here. He was nice enough to point out that actually the head of the NSA at one point was recommending EMET, was saying, hey, you know, this really helps us raise the bar in terms of our reaction to the attacker landscape. Definitely recommend going ahead and turning that on. So we have this tool that we've developed with all of our love coming out of the TWC team, Trustworthy Computing. People love it. People know about it. People are talking about it. Us being Microsoft, what do you think we did next? We decided to kill it. I feel like I can make fun of this because I was part of the team that actually made this decision. And I promise that this wasn't a decision that we made lightly or that we weren't taking into account the huge fan following that EMET had and all the goodness it had to offer. We made this decision to end of life EMET on the basis of really three main things. The first one is that EMET, because it was developed sort of outside of the Windows team, because it was developed as an extra toolkit that you run on top of Windows, it wasn't really developed with the same sort of engineering rigor that we maintain from within the Windows team. So think about things like performance, things like reliability. These are things that are ingrained into the Windows engineering mindset from a Gates perspective. And these were not things that were part of EMET at the time. The second thing, and we talked a bit about taking a trip down memory lane in terms of what was happening back in 2009, with Windows 10, we really felt that we had reached this pretty good release cadence. Now you see, first of all, we have our Windows Insider builds all the time. We have a twice-a-year release cadence. So we felt like we were in a much better position from a Windows standpoint to react a lot quicker to these evolving attacker trends. And then the third one, of course, going back to the core of EMET, really the thing that makes security folks really enthusiastic about this tool is really the exploit mitigations, the defenses that are part of this toolkit. And really, taking a step back at that time for Windows 10, we felt like we had a really good modern defense stack. We'd invested a ton of resources into building mitigations like CFG, Control Flow Guard, that actually superseded a lot of the mitigations that were included as part of EMET. And so we had this really measured response saying, hey, these are our reasonings. We believe that Windows 10 is your modern OS for this evolving attacker landscape, and we don't believe you really need EMET anymore. So with these reasonings, I hope that you believe me that we were sincerely not trying to troll our customers or EMET enthusiasts. We really felt like we had some sound reasoning behind this decision. So what do folks think was the reaction to this sort of announcement? Well, we definitely received things like, we don't disagree. Windows 10 is a great platform. You guys have really built it with security in mind from the get-go. It's releasing on a pretty decent cadence compared to how it used to be. But then we also received quotes like this. I picked a very friendly-looking picture of Will Dorman. He's quite famous in our hallways. And actually, interesting fact, both of these quotes are both by Will Dorman in the same article. The reason that this is interesting, and the reason it really caught our attention from the product team perspective, is Will was speaking on behalf of the CERT, which, as a lot of folks in this room probably know, is kind of taken as the gold standard of, what should my enterprise follow? What should my, big government customers, et cetera, think along those lines. So Will really took a step back, and he was like, I don't disagree. It's an awesome platform. You guys have built a really great platform here. But Windows 10 cannot protect insecure applications like EMET can. This is because of the big asterisk in the room. So he was mentioning things like, what about vendors out there that are not making use of all the applicable mitigations that they could be using? We ourselves are sometimes to blame about this here at Microsoft. But there's a ton of other vendors out there that are not necessarily using all the mitigations that might be applicable to their apps. And we have a couple of examples about this as well. Mark is going to show us one. The second one, which was really, really big, is what about apps that weren't built to use CFG? So I mentioned this awesome new mitigation that we had built. The one thing that I didn't mention is that in order to take advantage of CFG, your app actually has to be recompiled for CFG. Now, the problem that we were hearing is a lot of our customers were like, we can't recompile our apps. In a lot of the cases, we don't even have the source code for these apps anymore. These are LOB apps that we rely on. How are we supposed to make use of CFG? And now we don't have those other mitigations that EMET was offering because you say that CFG supersedes them, which it does. But again, they weren't recompiled. The third thing that he mentioned, which is a really interesting sort of concept, is EMET provided a lot of protection for what we call forever days. So these are essentially 0 days in unsupported products, which means that they never get patched, and so they're kind of there forever. EMET was a good stopgap solution for these kinds of things. We didn't offer anything along those lines anymore. And then finally, and we saw this from the Wikipedia entry, EMET had a cool GUI that allowed you to apply exploit mitigations to your system, to your apps. For those of you who've seen it, it's a big sea of checkboxes. It has a bunch of apps on one axis, a bunch of mitigations on the other axis. Where is this GUI? So this is really the birthplace of Windows Defender Exploit Guard. We figured, why let Weston and Sarhan have all the fun with App Guard? We made our own guard, so now we're part of the guards for Windows. And so this is a brand new set of host intrusion prevention capabilities for Windows 10, also introduced as part of the Fall Creators Update. So folks who are getting that update, you have a ton of goodness in there. And like this guy on my slide, Exploit Guard wears a lot of hats. In particular, we have 4 big features that are part of Windows Defender Exploit Guard that we feel is really a comprehensive solution, a comprehensive answer to the pain points that our EMET customers were having. So the first one that we have here is attack surface reduction rules. For the folks that are familiar with the ASR feature of EMET, what we tried to do is to make that feature a little more robust, a little more on the basis of behavior as opposed to blocking specific processes from loading specific modules. So we tried to make it a little more generic and behavior-based, based on what we saw, really, in terms of common patterns in malware, common patterns in the attacker landscape. And we'll look at a couple of examples of this just to make that really clear. The second feature, as part of Exploit Guard, is exploit protection. This is really your comprehensive set of exploit mitigations. We built that UI, and we built it better, I believe, than EMET did. So now you have a centralized UI to be able to turn on and off mitigations on both your system as well as on a per-app basis. And finally, we also brought in some of those mitigations in EMET that are superseded by CFG, which is a stronger mitigation, but we still brought them into Windows, understanding that there are legacy apps out there that cannot be recompiled for CFG that can take advantage of these. And Mark is going to give us a technical deep dive on some of those. Finally, just for good measure, we added a couple extra features into Exploit Guard, just so I can have all the hats. We have a third feature called controlled folder access. This is really about protecting your files, which are in key system folders, sort of preventing them from being modified by suspicious-looking or untrusted apps, including ransomware. And then finally, with network protection, what we've been able to do is we took the goodness of Smart Screen, now called Windows Defender Smart Screen, and we brought it all the way down the stack to cover all network traffic on your device. So all outbound HTTPS traffic. We will be blocking low-rep sites on the basis of hostname and domain with the network protection feature. Just because we don't have enough time, today we're going to focus, in terms of a technical deep dive, on the first 2 features here. But I definitely encourage folks to read up about all of them on TechNet. So first up, we have attack surface reduction rules. So now again, what we started with was EMET's ASR. We're trying to make this a lot more robust. We're trying to make this a lot more behavioral based. And I like to explain this with the help of an example rather than giving you a bunch of architectural lingo. So I like to start with this Office Files example. What we're really trying to do here is maintain a good balance between security and productivity, which is something that we believe is really important from the Windows standpoint. Of course, if security folks, if we had our way, we'd just block everything. But we want to make sure that our customers can actually do their jobs on our platform. So for this example, please put yourselves into the shoes of our well-meaning SecOps admin. He has been super proactive, reading up online, all the blogs, all the tweets, and he realizes, there's something going on in the attacker landscape these days that is Office-related. And I want to protect the endpoints in my organization from these Office-based threats. Can he block all Office usage within his environment? I don't think I see a lot of folks looking very positive about this, so that's obviously not possible. Now, the next step he takes is he's reading through some of these blogs, and he realizes, hey, a lot of these attacks seem to be mentioning macros. So maybe macros is something that seems to be sort of malicious. let me go ahead and block all Office files that use macros in my environment. So disable macros. We have a group policy that helps you do this. How many folks think that this is something that this SecOps admin can actually deploy in his organization? I see no hands, so either you folks are not listening, or you're right, because that's really hard to do. I mean, we tried to do that here at Microsoft. It did not end well. We got emails from the finance department. They were not pleased. So interesting story. The GP that I mentioned that lets you disable macros in your environment, until Windows Defender Exploit Guard, that was really the most granular you could get with this kind of behavior. That was pretty much your big hammer, pretty much your stopgap. What we're trying to do with the ASR feature of Windows Defender Exploit Guard is to take another step in and say, what is really the malicious behavior that is being displayed here? So what if instead of just blocking all macros, we could block Office files that are executing content? Or even better still, blocking Office files that are downloading content from the web and then executing that. So as you can see from the final oval here, it's very orange because based on our research that we've been able to do on our team, we see that the vast majority of files that are displaying this sort of behavior are in fact malicious. There are still definitely some of the teal colors, so some false positives, but for the most part, this is a pretty sort of suspicious behavior pattern. And that's exactly an example of what we might turn into an attack surface reduction rule. So you see, block Office apps from creating executable content. And so what you can see here, this is our initial set of 7 rules that we shipped with the Fall Creators Update. We're constantly looking to add more rules. We're constantly looking to even tweak these existing rules, which we can do. But what you see here is really that we're trying to block things on the basis of behavior patterns, which is a little more robust than just blocking specific modules from being loaded by specific processes. A quick word on how we anticipate that attack surface reduction rules can actually be deployed in your environment. We start, kind of like in my example, with either a proactive stance, so maybe I read this tweet from Taylor Swift on security, or maybe even a reactive stance. So maybe I'm seeing a bunch of breaches in my network based on my Windows Defender ATP data, and I want to do something about it in my environment. So you start from either a proactive or a reactive stance. You evaluate the rules that you have at hand, and you can actually turn on what we call an audit mode for these rules. So this means that the rules will be applied in your organization without any blocking behavior. And instead, every time we would have done a block, we write out an event to your Windows event log. Those events are also being channeled back to Windows Defender ATP to provide you an awesome one-stop shop unified UI experience. So the second step here, you can see a little snippet of the ATP portal is, of course, now that you've deployed those rules in audit mode, sort of reviewing the impact of, what would actually happen in my organization if I had turned this rule on. So now if you think back to my example about the finance department getting mad at us, we could have known that ahead of time if we had deployed audit mode, and then, of course, evaluated what the impact of turning those rules on would have been. And then finally, based on the rules that we feel we can safely turn on in our environment, we selectively flip those on. We have full support for your modern manageability stack, so GP, MDM, SCCM, Intune are all supported. I wanted to pick one real-world exploit example to show you guys how ASR can actually be put to good use. And so we're going to look at this one that was actually a really interesting case of Locky ransomware being installed on our users' machines via a DDE exploit. So what we start with here is socially engineered mal spam, so spam emails that Locky had actually rented a bit of the Nakurs botnet. So this botnet was basically distributing spam on their behalf. So you get an email that kind of looks like that little picture there. Looks like a pretty innocuous email. It has a Word document attachment. And these were very specifically targeted to folks, so they made this quite enticing in terms of a phishing attempt. Once the user sort of opens this Word document because they're curious about what they're being invoiced about, this is actually where we have this sort of malicious Word document that is leveraging the DDE attack vector. So for the folks in the room that aren't super familiar with what this is, it stands for Dynamic Data Exchange. It's very similar to macros and OLE in the sense that it's a legitimate feature of Office, and B, it helps you pull data from one document into another, or at least that's the intended use case. So when DDE kicks in, you see a dialog box similar to this one here, and we'll see that in a demo example in a second. Looks pretty innocuous. It doesn't really say anything scary. It's like, oh, I want to pull data from one location to another. Cool. Now, little do you know is that there's a hidden formula in this Word document. They actually did a really good job with it. They hid it on the second page of the document. So it's very not clear as to what's going on. It just looks like kind of a blank document. And what you see here in the black box is exactly the hidden formula that was in this document. So you can see the DDE call there. But instead of pulling data from one doc to another, what you see is we're trying to execute a PowerShell payload via cmd.exe. Now, what happens when CMD runs this PowerShell is it actually goes ahead and pulls down another file, so another downloader, and that too gets run via PowerShell. Now, what we're doing here is we're again reaching out to a bunch of URLs. That's really the C2. And once you reach out to those C2, you end up downloading the Locky ransomware binary. It's encoded. It gets decoded on your local machine. And I think everyone else knows the end of the story. The files that are stored on your local hard drive end up getting encrypted. You see a scary message like the one over there. That's actually going to be your desktop screen. Scary. Now, if you think back to the slide that we looked at with the example ASR rules, one of them was called prevent Office from opening child processes. Now, imagine a world in which this rule was enabled. Essentially, only the first two stages of this attack are applicable, because the first one is, of course, the mal spam is going out. Doesn't really affect that piece. Of course, I can open that Word document. That works fine. But as soon as Word tries to open that CMD that you remember from the hidden formula, it can't, because it's being blocked from opening child processes by this rule. So let's take a look at what this looks like in practice with this demo video. So that's the email. You see my user, poor thing, opening this Word document. The first page is empty. Protected view is up there to protect you, but doesn't. We go ahead and click through this DDE message prompt because it doesn't look terrifying enough. And now we're saying something about some inaccessible data, but we see that block down there. Fun fact, that notification is fully customizable, so any SecOps person can kind of put whatever text they want in there. What you see here is the hidden formula that we took a look at that's very cleverly hidden on the second page. And as I promised earlier with audit mode, we also write out these logs when you're in block mode, so you can see that log written to the console, to the Windows event log over there that proves that I wasn't lying. And then one final quick note before I hand over to Mark to talk to us a bit more about the exploit mitigations as part of exploit protection. We're seeing a really cool trend, and let's just take this one rule that we've been looking at as an example, which is prevent Office from opening child processes. Word, especially as part of Office, seems to be being used as the sort of delivery method du jour these days of a bunch of targeted attacks. And so what we're really seeing is that some of these rules can be very effective in terms of zero-day neutralizers, so blocking sort of exploit attempts before there's even a patch for that. So I have a couple of different examples here. This CVE, and actually these CVEs are all in different products. So this CVE is a CVE in .NET, but in this case, Word was used as the initial sort of delivery vector. The payload that was downloaded to the victim's machine here was FinFisher. So this is sort of a commercial surveillance package for those who are familiar with it. But in this case, again, if you had that no child proc rule turned on, this would not have been effective. A second example. This CVE is a CVE in Adobe Flash. So again, nothing related to Word, but Word is being used as that sort of delivery vector. The malicious Flash was embedded via ActiveX into this Word document. The final payload for this, which was actually turned out to be the Black Oasis campaign, final payload was also FinFisher, so surveillance. These are very highly targeted attacks. But again, with child proc turned off, Word can't open that Flash object, so you're safe there. And then finally, this CVE is actually a CVE in Office, but it only applies to legacy Office, so 2010 and earlier, the ones that were not compiled with forced ASLR turned on. This was also seen exploited in the wild, delivered via RTF in this case. But again, you see that same exact rule being able to kick in over there, protect you before the patch is even available. Final payload in this case was also a rat tool, essentially. So with that, I promised I would hand over to Mark to talk to us a little bit about exploit protection, which is our second hat.
Thank you. Right, so as Jessica mentioned, exploit protection is the second piece of Windows Defender Exploit Guard, and it's kind of the functionality that allows you to apply mitigations to applications and kind of replace EMET. So what we had in Windows 10 before the full Creators Update, as the result of a long evolution of security mitigations in Windows, is a whole bunch of platform mitigations that were available for you to use. Things like DEP to prevent you from executing code on the heap or data on the heap as if it's code, ASLR that randomizes where things are loaded in a program, CFG, ACG, all of these kind of low-level mitigations that could be turned on. And as Dave Weston and Sarahan mentioned in the previous talk, a lot of these mitigations are applied to inbox components in the operating system, to the Edge browser, and to IE to make them super secure and hard for attackers to exploit. But we didn't really have a good way for users to go and configure them for their legacy applications that they wanted to protect. They were hidden away in the registry behind a kind of very opaque registry key, and it was not easy for people to actually enable them. We also didn't, before the full Creators Update, we didn't have a way for users to enable these in an audit mode and kind of try them out, see what would break, see if their enterprise could actually be protected with these mitigations without impacting productivity. So what we wanted to do in the full Creators Update as part of kind of filling this hole that EMET being end of life created is have an easy way for people to configure these existing inbox mitigations for their legacy applications and also use audit mode to try them out and see what would work and what wouldn't work. So we did a bunch of work kind of on these existing mitigations. But obviously, that wouldn't be good enough to really make up for EMET being end of life. So we realized that for some of the mitigations EMET provided, we really needed to add them inbox in Windows. They do provide value for legacy applications that can't be rebuilt with CFG and can't be recompiled to use the latest mitigations in the OS. And while they're not perfectly secure, they do add value, and we do want to allow people to use them as a fully supported inbox feature in Windows from now on. As part of that work, we also added a new mitigation. So it's kind of even better than EMET was. We didn't just directly port what was there. And we really looked at kind of what was the overall state once we added these and only ported the EMET mitigations that make sense and actually add value in the modern kind of exploit landscape. We didn't port everything like the anti-heap spray and some mitigations that really don't add value in 2017. So I'm going to kind of talk about a real exploit example that shows how these mitigations can be used against a legacy application. I'm going to be using Firefox because it's a good real-world case. There was an exploit discovered in the wild, a real zero-day. It was actually discovered in 2016 in November, targeting the Tor browser, which people use to browse the web anonymously. And Firefox kind of, back then, didn't use a lot of the latest security mitigations that were available in Windows. So even if you're using Windows 10, it was relatively easy for an attacker to exploit Firefox. The good news is that Firefox responded very quickly and patched this. So for the demo, I'm going to be using, obviously, an old unpatched version. And Firefox is moving forwards and adding new security mitigations in the current version. So I don't want to beat up on them. This was a point in time more than a year ago. And they've made great strides in terms of security. But this is a good kind of legacy application type of view that we can demo. Obviously, the Tor browser is a juicy target for people to go after. So being able to apply mitigations to browsers and processes like this, or things that are targeted, is something that users want to do because they know that people have a lot of money that they're actually targeting in terms of researching and developing exploits for products like this. The bad guys out there, if they want to get you and they have enough money, they're probably going to be able to put together a working exploit. And the more mitigations that you can enable, the better off you're going to be. So the vulnerability that I'm going to be demoing is this CVE, which was a use after free in the Firefox SVG animation code. As I said, it was discovered in the wild and then patched within a month by Mozilla. The targeted machine is going to be using an old version, and I'm going to be running Metasploit's kind of existing exploit library to target the vulnerable machine. And just to have something visible that you guys can see when the exploit succeeds, I'm going to be launching calc.exe, so that familiar attacker payday of having the calc pop is going to be the payday. So before we actually go through and look at the video of the demo running, I wanted to kind of walk you through what the exploit is doing under the covers so you can kind of understand the kind of steps that the attacker had to go through to get their code execution to work. And a lot of these steps are kind of the things that people would be doing if they were attacking Edge or Chrome as well. They may have different app container, sandboxes, and things they have to bypass. But a lot of these techniques are kind of what modern attackers have to do to exploit programs. We can then look at the different stages and see where the mitigations have a chance to block the exploit. So initially, the vulnerable browser is going to be loading a web page that the attacker controls. And JavaScript that the attacker has written is going to trigger this use after free condition. So some heap memory is going to be freed and replaced with attacker data, but the program will still think that it has its objects that it is allocated sitting there, and it's going to try and use them. When that gets triggered, the attacker then has what's called an arbitrary read primitive. So they corrupt something like an array, which effectively, by corrupting the length, allows them to read anywhere in process memory, and they can even write process memory using this. So by reading memory, they can then break ASLR. And ASLR, if you remember, is the thing that randomizes where DLLs are loaded in the program. The attacker needs to know where things are loaded so that they can start piecing together code that they're going to be using later on. So by reading memory, they find this one DLL that Firefox has called XUL. And from that DLL, they then go and they look and see what APIs are imported. And they know that for their exploit to work, there are some system APIs they want to be able to call that NTDLL implements. But instead of getting them directly from NTDLL, they're going to basically kind of do a level of indirection and go to this Firefox DLL that imports those APIs and use that import table as a way to find them. Then once they have those APIs, they can start putting them together in kind of a ROP gadget payload. And this is basically stitching together existing code in a binary in a kind of unexpected way, so it'll execute what the attacker wants it to do and actually give them code execution. They'll fill in a heap memory with that ROP payload, and then they'll trigger what's called a stack pivot. So normally your thread has some memory which it's using for a stack. The attacker can pivot that and actually make the stack point at this heap memory that they filled in. And now return addresses and parameters for function calls will be coming from the attacker's heap data. So this is all happening in JavaScript in your web page. When that stack pivot is triggered, we're now executing the ROP payload that the attacker has filled in. And it's going to start invoking some APIs that they found from NTDLL, which are designed to make memory in the process executable, because by default with DEP, your heap data is not executable. Once it is executable, then they can just jump into that shellcode and do whatever they want. So the shellcode payload, then it has some actions it wants to do. So it's going to find APIs, like maybe it's going to download stuff from the internet, maybe it's going to create a process. It's going to find those APIs using export tables, typically. And then it's going to invoke the APIs and profit. The attacker's job is done. So if you look at the whole view, where do the exploit mitigations and the payload restrictions, like the EMET mitigations, where would they actually have a chance of blocking this exploit chain? The first place where they can kick in is this first step of resolving APIs using the import table. This is where we added a new mitigation in the full creators update, which is called import address filter. And we'll talk about that in kind of more detail and kind of see why we added it and how it works. If that was bypassed or not enabled for some reason, then the next place we could actually block the exploit is on the ROP execution, the initial ROP execution. So when those APIs start being invoked from ROP, the anti-ROP mitigations that we ported over from EMET would take effect and block it. And then lastly, when the export tables are being used to locate APIs, the export address filter mitigation would kick in there and can block the exploit at that point. So now you have an idea of kind of what the exploit is doing under the covers, and these three mitigations can be used to detect and block the exploit. So for demo purposes, what I'm going to be doing is showing you a live machine running the exploit. I'm going to do it kind of in 3 steps because we wanted to show each of these mitigations firing in turn. Normally, if you're an admin rolling this out in your enterprise, you would turn on all the mitigations at once. You'd kind of enable the most secure state you could. And whichever mitigation triggered first, so in this case, it would be import address filter, that would block the exploit there, and you wouldn't see the other two fire. Because we want to show all three, we're going to kind of do them one at a time in the video. So let's start the video, and we're going to run Firefox on the victim machine. And go to our attacker URL. And as you can see, we have calc pop when the exploit succeeds. So we don't have any mitigations configured. This is sort of out-of-the-box state before you configure anything. So now let's go and actually use the UI that we added to Full Creators Update in the Defender Security Center to go and configure the mitigations for Firefox. You have to kind of scroll down, go to Exploit Protection Settings. And here we have system settings shown initially, which are applied system-wide. But we want to add program settings specifically for Firefox. So we're going to add a new program, put in the binary name, or you can browse to a specific application. And then we have this window that pops up with all of the granular mitigations that can be applied for Firefox. We're going to scroll down and find the export address filter mitigation and turn that on. And then EAF Plus is kind of an extra mode that we checked there as well, which EMET's mitigation EMET had. Now, if we rerun Firefox and go to our attacker website, we will see, hopefully, what's going to happen. But first, when it does trigger, we, as I said, have audit events that get generated on the machine. Jessica mentioned this. In the event log, they get stored under the security mitigations user mode folder. And we have nothing there yet because we didn't actually run the exploit with mitigations turned on. Let's try again and see what happens this time. We see that the application has stopped working. And here we basically have a crash that Windows error reporting is picking up. And if we look in the event log, we see we have our event for export address filter catching access to NTDLL's APIs. So success. And if we look in the application log, we can see we have crashes and WER events. So we actually get some telemetry from these crashes we can look at to see what potential exploits are we actually blocking in the wild if customers turn this on. And we can see a DLL is being loaded into the process to implement the mitigations. That's what triggers the crash. Now we're going to show you using enabling the other mitigation, import address filter, and we're going to use PowerShell instead, which is another way to configure and view settings on a machine. So we have some PowerShell command that's where we can basically add mitigation options for a process. And we're going to enable the import address filter mitigation this time. So this will be enabled in addition to export address filter that we had already. So if we run the get command, we can see the state now we have import address filter turned on, and above at the top you can see export address filter. Let's rerun Firefox again, go to our attacker website, and we'll see very similar kind of flow as before. We'll have the crash be triggered, and if we look in the event log this time, we'll have a new event that's been added there for the import address filter mitigation triggering. And we can see that the API that the attacker was trying to find was load library, and we can actually figure out which API they were looking for. So lastly, if we want to enable the anti-ROP mitigations, again in PowerShell, it's just a case of using the enable option and then putting in the additional mitigation names. And we can comma separate them if you want to do multiple ones in one shot. Turn those on. And then we're going to actually disable import address filter because it would block the exploit before it does the ROP execution. So let's turn it off. And see, everything's turned on as we want it to be. We can rerun Firefox. Boom. All right, so we have some more crash events, and we have our events. And the events are written in audit mode and enforcement mode, so you can kind of see in both cases. Right, so that showed the 3 exploit mitigation options actually protecting Firefox in this case. If you are using Windows Defender ATP, if your enterprise is using that, then all of that telemetry that we saw in the event log is actually being collected by the agent on your machine and sent to the cloud as well. and is visible in the machine timeline. And we have detections that will actually fire alerts if we see any exploit indicators from exploit guard. So here's an example of the Firefox attack that we saw where exploit guard is blocking the exploit due to exploit address filtering. And in the timeline as well, we can see for the ROP mitigation, we can see an event in the timeline for the ROP exploit. We can see virtual alloc was the API that was being executed by ROP when the mitigation check happened. And then here for the import address filter, again, we can see load library EX was trying to be located by the attacker. We blocked that and stopped the exploit. So Defender ATP is really a good way to collect all its telemetry in audit mode or enforcement mode, detect real exploits once you've configured this for your enterprise, and kind of manage your whole fleet of machines that way. So let's have a look and see what is actually happening under the covers, how these mitigations implemented. And a lot of this was ported from the way EMET implemented them, but we did make improvements to make performance better, kind of improve app compat, and actually make the mitigations a little bit harder to bypass because there were some known bypasses for EMET that we wanted to try and address wherever we could. So the attacker originally, their kind of foothold in the process is to get code execution somehow, triggering a UAF or doing some exploit. And their goal is to find APIs that they can then execute as part of their exploit chain. They first need to find out where those modules that they want to invoke are located in memory. They have to break ASLR. And the way they do that currently is by information leaks. So reading arbitrary addresses in memory, finding where things are, and grabbing stuff that way. Especially in the web browser, because you have so much power with a scripting engine at your disposal, this is a very powerful primitive for attackers to have. So let's say the attacker is now scanning the module list that's loaded in your process, and they're trying to find NTDLL because they want to call the APIs that are exposed by that binary. Once they find NTDLL in memory, they can then start walking the actual image data and parsing the DOS header, the PE header, optional header. It has a data directory with all of the different sections. And the one that they're interested in is called the export directory, which has a list of all of the APIs that are exported. Once they find that, kind of their goal is pretty much achieved. They can look at the table and find whichever API from the string name. When they find a match, they can then grab the address for that API, and then they can use it in their ROP payload, or depending on what primitives they have, they may just be able to execute those. So attacker goal has been achieved. They know where these APIs are in memory. We want to block that somehow. So how did EMET actually block this initially, and how do we do it in Full Creators Update with the built-in EMET support in the OS? The way we do it is by actually changing protections in memory for critical system DLLs like NTDLL, kernel-based, and kernel32, because we know these all export APIs that attackers want to target. They give them functionality that they need as part of getting their payload running. So changing memory protection, creating processes, loading DLLs, all of these bad things. If we can block them from looking at the export directory for these 3 system DLLs, then we can kind of put a roadblock in their way in terms of their exploit executing. So a guard page protection, in case you may not know exactly what that is, this is an existing protection that the memory manager in Windows supports. And it basically allows you to say, if anybody touches this part of memory, trigger an event, and we have a vectored exception handler which will actually be invoked at that point. And we can then see who is trying to touch that memory. We can inspect who it is. So if the attacker comes and tries to look at the export directory for, let's say, NTDLL, it'll trigger the guard page exception. Our code will then take control of the thread in that process. And we can inspect and see, OK, who's reading this export table? Is it a normal, valid scenario for looking at the export table? Because there are normal use cases where this happens. Or does it look suspicious? Does it look like an exploit, and should we block it? What is suspicious? Well, if there's code running on the heap and outside of any loaded module, that's pretty much an obvious bad sign. We should block that. If it's a valid valid DLL, like let's say it's javascript.dll that's touching the export table, that may be OK. But if JavaScript or VBScript are doing it, usually that indicates that the attacker has corrupted memory in such a way that they can use JavaScript to do kind of like a reader gadget operation. They can make JavaScript code read anywhere in memory using actual code in JavaScript. So we call those suspicious reader gadgets, and EAF Plus will try and detect those and block them. Or then we can actually see, like, are you doing some kind of ROP execution where the stack is pivoted to the heap? So that's great. Yeah, EMET had EAF, and we ported that over to full creators update. But it's not really good enough in terms of modern exploits. And we've seen real, in the wild exploits, exploit kits like Angler, where EMET is being used by more and more people, and they want to actually have their exploit work even if EMET is there. So they found a way to bypass EAF. How did they do that? Well, the FireEye guys that discovered this when they did their blog, they looked at it, and the actual payload that was being used did something sneaky where instead of looking at the export address table, they used the import address table, kind of like what I was showing you in the Firefox exploit as well. And because EMET was not kind of designed with blocking this technique, it wasn't part of the original design, there's no guard page protection, and this access is allowed, and the exploit is able to get the APIs they want to call. So we wanted to see if we could raise the bar in terms of the protections that EMET could provide when we added it inbox. So we thought about how could we break this import address table technique. And the way that the OS works, when you have a DLL loaded into your process, your DLL, module X in this example here, it could depend on some other APIs that other DLLs expose on the system. And the operating system is responsible for loading your DLL, and then any of your dependencies will be loaded as well if they're not there currently. And the loader will fix up your dependencies by kind of finding out, oh, you depend on, let's say, load library. In your import descriptor, you have an entry that says, I need some APIs from NTDLL. Please go and find them for me as part of loading me and fill them in this table. And once you've filled them in, the OS does this itself. The code can then just use these addresses to call the APIs. So this is the normal operation of the import address table. Looking at this, it's kind of not immediately obvious how you would block this, how you would have a mitigation to protect it. So when the attacker is kind of looking at the import table, they're directly finding these bound import address entries. How can we break that? So I kind of simplified things a little bit for the diagram here. The way it's actually implemented, if you look at the PE kind of spec and the format, is that these strings for the API names are not kind of directly in one table. There's actually a set of pointers or relative virtual addresses in the binary that point to the string data. So for all of the APIs that, let's say, you need from NTDLL, there'll be different pointers to each of these strings. And the loader will go and look at the string and then figure out, OK, how do I find that API and get the right address for you? So we know that attackers are looking for sensitive APIs that they want to call in their exploit. And we can have kind of a bound list of these sensitive APIs that we want to detect and block resolution of through the import table. For the ones that we care about, we can do something sneaky, and we can actually redirect these pointers or relative addresses. Instead of having them point to the string data in the DLL, the way it would normally be, we can point them at some memory that we allocate as part of the mitigation, create something called a shadow table, shadow import table. And the shadow table will have basically the same data. It will have the same strings. It will have the same bound import addresses. But because we allocated, we can control the protection. And anytime this is accessed, it's kind of suspicious, because normally this kind of import resolution is done once by the loader at the beginning of the process. So if we look at especially the strings are looked at once and then not looked at again. The addresses are looked at all the time whenever the application calls these APIs. So we can put the guard page protection approach to work here again and protect this whole shadow import address table using the same mechanism. So when the attacker now tries to walk the import address table and look at these strings to find APIs they want to use, they trigger that guard page, and we can then go and inspect them again the same way as we did for export address filter and block them. So that kind of gives you an overview of kind of how the mitigations work, kind of at a high level, but understanding what's happening under the cover. The anti-RUP mitigations that we have were ported from EMET without too many changes. And I'm not going to go into a lot of detail about how those work. But the way that EMET kind of implemented it and we preserved is by triggering checks for RUP mitigations through API hooking. All of those sensitive APIs, and the APIs are pretty similar between import address filtering and anti-RUP. We want to basically trap any call to those APIs and check them using 3 checks. So the first check will check for stack pivoting, where the stack pointer is pointing outside of the usual range. Next check, caller check, will see if the return address on the stack is not preceded by a call instruction, which we would normally see for a normal invocation of an API. And then the third one, which is kind of the most complicated one, does a forward simulation. So when our targeted API returns, what does the stack have in terms of return addresses, and do they look suspicious? Are you chaining together very short snippets of assembly or machine instructions with lots of ret instructions, which is what a ROP exploit typically would do. So that was a quick blast through kind of what exploit protection does, how it works under the covers. Thanks to all these folks and the teams that worked on EMET and Exploit Guard. And now I'll open it up for questions if anybody has anything. Thanks.
Thanks for such a great presentation on whatever became of EMET. So it's great to see how we move from sort of a conceptual product into something that actually has real value to people using modern OSs. So we have time for just a couple of questions because we need to prep for the next session. So let's take 2 or 3 questions depending on the length.
Yeah, so regarding the integration, this side.
Okay, see you.
Okay, regarding the integration with the ADP, you mentioned about the exploit guard. It mentions that these files have been kind of found by the exploit guard. Now, there's an option over there from the ADP perspective wherein we have to block the file through the Defender AV. That has a requirement wherein you have to have the real-time AV across the board on all the endpoints. Are you guys thinking that any kind of integration with the exploit guard wherein you can block the file on those endpoints, any kind of signal exchange through ADP in the future?
So I would say that the blocking of file functionality that you're describing from the ATP portal, I would see that as sort of orthogonal to the features that we described today. One good thing that you pointed out, though, is that feature does require Defender AV to be the active AV on your machine. Out of the 2 features that Mark and I described, the one that I talked about, attack surface reduction, actually also has a similar requirement in that we're using Defender AV to perform the blocking on your client machine. All the stuff that Mark described, though, is built into the operating system, does not require AV intervention at all. So the blocking would take place on the client. But what you see on the ATP portal is, hey, this was blocked, or this would have been blocked, it's in audit mode, that kind of information. So the blocking itself is happening on the Windows machine. But you do see that data back on the ATP portal.
And we're going to take one more question right over here.
So my question is, all the mitigation steps that you have, is there a way to plug in for somebody that's not a part of your team? I mean, what is the extension mechanism? Is there one?
We don't really offer an extension mechanism to add new mitigations to the OS this way. It's kind of, I guess we're going to be looking at if there are any bypasses or new exploit techniques that come up in the wild that we need to respond to. We can then use our regular, like twice a year or Windows Insider preview program as a way to kind of quickly improve mitigations to cover that. But we didn't build it as kind of a generic platform where third parties could add new mitigations to the OS.
A big thank you to Jessica and Mark for the excellent tour of defense technologies inside Windows 10.